All right, class. So let's get started. I ended class on Wednesday talking about that example where I was driving from here up to LA, and the question that I asked was what my average velocity was. And I ended class by calculating what my average velocity was. It ended up being 73 1/3 miles per hour for my trip from UCSD up to Eagle Rock in Los Angeles. And we calculated that by dividing the total distance, 110 miles, by the total time, which it took me 90 minutes, famously so 1.5 hours. And what I want to point out now is another way to write this. Because we already learned how to calculate this number on the top. That's an integral. That is a displacement, actually, which back in, 5.6, I gave you guys a formula for displacement. So if you recall, the way we could have gotten that number, that total displacement, is by integrating my velocity, starting from time equals 0, ending up at time equals 1.5 hours. So that gave us the total displacement on the top, and the number on the bottom is, I could write that as 1.5 minus 0. And there's a special reason why I'm writing this in this way. This is actually a quite general formula for any time you want the average of some function. In this case, it was the average of this function, the velocity. But we can actually apply essentially the same formula to get the average of any function. Any function, let's say f of t, on some interval a to b. And so if you can look at this expression and sort of compare, here this was my f and these were my two endpoints a and b. The average formula, the formula for the average is 1 over b minus a times the integral from a to b of f of t dt, right? So in my example, f was v, a was 0, b was 1.5. A little aside while we're talking about velocities. There was something that I skipped in the first week and that I probably should have spent a little bit more time on, because I think for some reason I thought that you guys had already done it, but it was brought to my attention that maybe some people hadn't quite had the distinction between speed and velocity clarified. So just for completeness sake, I know you guys already did the homework on it, so it's kind of maybe a bit too late now. You probably had to figure out yourself that displacement equals the integral from, let's say, t0 to t1 of velocity of t, while the distance traveled during a trip, you don't integrate the velocity, you integrate the speed. So you need an absolute value sign there. So typically on a problem, if you have to actually calculate a distance traveled, you've got to deal with these pesky absolute value signs. And so you guys probably remember having to split up an integral into the parts where the integrand was positive and the parts where the integrand was negative. That's pretty typical for a distance calculation. So just to illustrate this, if I toss this chalk up, nice. What was the displacement there? Zero. Yeah, it landed right where I tossed it from. The distance, though, was about, I don't know, went up like 10 feet. So about 20 feet of distance traveled. So that would be a typical calculation there. But I just thought I would point that out. Now let's get back to this. Let's get back to talking about averages, though. Now, I claimed that this was the formula for the average of a function. And hopefully, you believe it because it seemed to make sense in this example where my average velocity in driving up to LA was 73 1/3 miles per hour. That doesn't really prove it, though, so how about I prove it to you guys? So recall from anyone that's taken, I don't know, very basic statistics, if you have a bunch of numbers and you want to get their average, you add them all up and divide by the number of numbers. So let's say we have some numbers a1, a2, out to a sub n. Then the average, it equals, we add them all up, and then you just divide by however many you added up. Okay. And let's write this maybe a bit more compactly as sum from I equals 1 to capital N of a sub I. We would call this a discrete sum because it's a sum of n discrete values. So now let's start trying to pass to the continuum case, as we would say in calculus. Yeah. So now consider f of x on the interval a, b. And let me try to draw this. Let's say here's a, here's b. There's y equals f of x. And I'm going to split this up into a bunch of subintervals, into n subintervals, where each one has width delta x, which is equal to what you would get if you took the length of the whole interval and divided it into n. So there's n of these subintervals. And any particular one of them, let's say the ith one, we can calculate what the value of the function is right here. And that's going to be f of xi. Okay, so let's take the value of the function at each one of these. This is x1, this is at f of x2, this is f at x3, xi, and so forth. So the average of all these different numbers, f of x1, f of x2, so forth, up to f of x capital N is, well, it's this same formula right here. It's the sum from I equals 1 to n of f of xi divided by n. And now comes the cool part. I'm going to do this little trick where I'm going to multiply and divide by the same quantity. So this is equal to the sum from I equals 1 to n of f of xi over n. And how about I multiply and divide by delta x? Let me write it like this. So I'm going to put in a delta x here and also put in a delta x here. It's the same thing, so I can do that. But n times delta x is n times, you can see I had an expression for delta x. It was b minus a over n. So we get to cancel these guys, and we just get b minus a. So this whole thing is equal to the bottom is just b minus a, and the top, well, is still the same thing. Does anyone recognize what the top looks like, though? Yeah, that's exactly the Riemann sum approximation of the area, the integral from a to b. So, taking the limit as capital N goes to infinity, so the width of each interval goes to 0. We just get exactly what we want, the integral from a to b of f of x dx divided by b minus a. So there's your proof. Now, let me talk about an important application of this proof. And let me put it in terms of that trip that I made to LA. So we decided my average velocity on that trip was 73 1/3 miles per hour. I claim that there had to have been a time, at least one time on that trip, where if I looked at my speedometer in my car, it said 73 1/3 miles an hour. Assuming my speedometer displays thirds, but that's beside the point. So you guys agree there's no way I could have, for example, I could have gotten from here to LA without at least going at this speed at some point, right? Like if I'd been slower than this the whole time, I couldn't have had this as my velocity. And if I ever went faster than this, well, you speed up continuously. You can't just discontinuously jump from a lower speed to a higher speed. At some point, I had to have actually been going this speed. And in fact, if you look at the graph that I drew for my velocity versus time, which looked like this, according to this picture, about how many times did I hit this velocity? Yep, 4 times. Once when I was getting on the freeway, once when I was slowing down for the checkpoint, once when I was speeding up away from the checkpoint, and once getting off the freeway. So in this case, there were 4 instances, but there will always be at least one where the mean value is attained, and this has its own theorem. It's called the mean value theorem. So the mean value theorem states that for a continuous function f of t on AB, let me continue this over here. there is at least one point C in the interval AB where the average is attained. I.e., at that point, f of c is equal to the average value, which we said was 1 over b minus a to b, f of t dt. The mean value theorem might seem a little bit familiar. Does this remind anyone of another theorem that maybe you learned in like algebra or something, or pre-cal? It's like the who said that? Who said intermediate value theorem? Yeah, it's like the intermediate value theorem. This is like the calculus version of the intermediate value theorem, kind of. You prove it using the intermediate value theorem, which I'm not going to do. But yeah, it's basically, it comes down to the fact that like there's no way I could draw a line from this point to this point without passing through points in between them. All right. Any questions before we start doing volumes of revolution? And now, I'm not talking about, social movements. I'm talking about cylinders, vases, coffee cups. So let's do 6.3 volumes of revolution. So the thing about 6.3 is it's actually not really anything new. I'm not sure why it needs to have its own section. Well, I know. It's because it's a particularly important example and application of what we did in the previous section, which was solids. So 6.3 is specifically about solids that you get if you revolve some shape around some axis. Probably should have brought more demonstrations today. I left my knife at home. I was thinking I could use an apple corer because that would give me like a hollowed out sphere. So I was sitting thinking about, okay, so what sort of physical demonstration can I do for volumes of revolution? And I was thinking and drinking my coffee and thinking, and the whole time, like my cup of coffee was just sitting right in front of me. This is a volume of revolution. So I realized, yeah, let's just calculate like what the volume of this cup of coffee is. And so that'll be my first example. So these guys, they're solids formed by a region in the plane around a certain axis, which is often the x or the y axis, but it doesn't have to be. Sometimes it's maybe the line x equals 5 or y equals 10. It kind of depends on the problem. It's always parallel to at least one of those axes, though, thankfully. So right, these shapes look like here. Let's say if I took this shape and I rotated it around the x-axis, it would look kind of like a football. Okay? So that would be an example of what would happen if we took this orange region and then rotated it. We can still use the same formula that we already learned in 6.2. Which was, it was the integral of the area, the cross-sectional area. Say f of x dx. Or c to d a of y dy, if we end up integrating dy instead of dx. So if you've got some good physical intuition, can you guys tell me what shapes are the cross-sections going to look when it's a volume of rotation, of revolution? Circles, yeah, these are all going to be circles, actually. Later on today, I'll do like hollowed out volumes, which are, in that case, the cross-sections are technically called annuli. That's the plural of annulus. It's like a bigger circle minus a smaller circle, or it looks kind of like a washer for those of you guys that do a lot of construction. I think I'll just do my example with my coffee cup right now. And you can kind of just get the idea by seeing the example. So, I was trying to think of a funny reason why we would want to calculate the volume of a coffee cup, and I didn't really think of a funny one, but if someone comes up with one, let me know. So here's the picture. It looks like all right, and so there's a cross section, say at height y. And let's put some dimensions on this guy, this gal, on this cup. It's a bit not quite drawn the same size. Let's say this is 2 inches right here. And let's say the top okay, yeah, that looks about right, at least on the board anyway. That is about 2 inches. That's about 3 inches. And let's say it's about 6 inches tall. So we want to get the volume of this shape, and the cross section is going to be this disk, which has area A. I'll call it A of y because, as you can see, it's going to depend on y. It's equal to pi r squared, where r is that radius. So now is probably the hardest part of the problem, is to figure out what this radius of that disk is as a function of y. Any ideas how we could do it for this one? And also, maybe I didn't say, but it should be kind of apparent that we're going to be doing a dy integral, that because disks are perpendicular to the y-axis. All the symmetry is along the y-axis, so we definitely want to do this integral dy. And who's got an idea as to how we could get the radius as a function of y? Well, what did I do last time? When I did the pyramid, I used similar triangles. I could do that. I don't really have the triangle, but I could like finish drawing this thing, and I could get like a big triangle down here. But yeah, I already did a method using similar triangles. Let's do it using coordinate geometry. So I can label some points on the graph here of this line right here goes through the point, this is the point 3, 6. This is the point 2, 0. The slope of this line is, let's see, it goes up 6 and over 1. So the slope is 6. I can use slope-intercept form. The slope-intercept form says y minus y1 is m times x minus x1. So here it'll be y minus, I can use either of these points. Let's use the bottom one. Y minus 0 equals 6 times x minus 2. Did I do that right? Okay. So y is equal to 6x minus 12. And now looking back at the red disk right here, the radius of this disk is exactly the x-coordinate of this point. So if this is the point xy, then r is equal to that x-coordinate. From this expression, we can get that 6x is equal to y plus 12. So x is equal to y plus 12 divided by 6, which is equal to y over 6 plus 2. Great. So r as a function of y is y over 6 plus 2. Then, okay, now this problem is pretty much just like the volumes of revolution. The solids that we did in 6.2. So a of y is pi times y over 6 plus 2 squared. Okay, up to 4 empty boxes of chalk. Now that I've got the cross-sectional area, I can just do my integral. The only thing that I haven't figured out yet is the limits. Anyone see what those are? From 0 to 6. Yeah, so we're going to start at y equals 0 and go up to y equals 6. This is my volume. I guess I can just finish this calculation. It's not so bad. So this is equal to pi times the integral from 0 to 6 of, hey, last time I did u substitution. How about this time I just multiply it out just to show you that there's a different way that you could do it. You don't have to use u substitution. It's just kind of smart. So this will be y squared over 36 plus y over 3, 2y over 3 plus 4. So that's pi times, let's see, we'll get y to the third over 3 times 36 plus 2y squared over 2 times 3 plus 4y from 0 to 6. This is equal to pi. Okay, 6 to the third over 3 times 36 plus, cancel these guys, 6 squared over 3 plus 4 times 6 equals pi. Let's see, 36 cancels out with that, gives a 2. 36 is this, 18. Okay, so I get 2 plus 18 plus 24 is 44 pi. 44 pi inches cubed. How's that look, guys? Anyone catch any mistakes? I do usually make a lot of sort of trivial, careless mistakes, so remember, I told you guys, see if you can spot them. So let's just write down what the general formula here is for these guys. So we will have, for example, if we're integrating in the x direction, it'll be the a to b times pi times the radius squared dx. Okay, I think I've earned myself some coffee now. Mm-hmm. Sorry? Oh, is this, oh, this 12? Oh, okay, thank you. Yeah, all right, thank you. Yeah, this should be a 12. All right, 48. Is that what you're saying? Okay, thank you. Cool. Oh, 14 plus 24 is 38. Thank you. So I said we could also do hollowed out volumes of revolution. My physical example for this one is like a wedding ring. So let's say, I don't know, you guys still plan on getting married? Like, it's kind of antiquated now. Who does, what, like for the tax benefits? I don't know why. Like what, if you love someone, just like stay together. Why do you have to like get a legally binding contract for that? I don't get it. But let's say you wanted to get someone a marriage band, right? A wedding ring. Now, for the engineers in here, a lot of you guys are planning on being engineers, so I assume you're going to do a lot of computer-aided drafting, CAD modeling, 3D printing. You can design your ring now. So this is kind of going to be like that, actually. Let's say you want to design, this would be like the nerdiest wedding proposal ever, is the ring that you made. So let's design this ring. Here's how I'm going to set it up. Okay, I'm going to draw a few functions in the plane here. The first one is going to be y equals 1/2 x squared. And then I'm going to truncate that. Say if this is 1, this is 1/2. Right here. So let's take this shape right here, and I want to revolve it around 1, 2, 3, 4. I want to revolve it around the line y equals 2. So the shape, it's going to look like this. A little bit like an olive. Okay, so in this case, what do our cross sections look like? If I slice this guy, say that this is some point x, and I just cut this ring, the cross section here, okay, so it's going to like have an inner part and an outer part. What does that cross section look like? Yeah.
I have a question.
Mm-hmm.
How do you know whether you want to cut it x-wise or y?
Yeah, that's a good question. So what's the axis of symmetry here? Or so what's the axis? How about what's the axis of rotation?
Y.
It's revolved around this line, y equals 2. Okay, so our axis, it's the line y equals 2, but it points like in the x direction. So like in the coffee cup, our axis was vertical. So this was appropriate. That's why it was appropriate here to do a vertical, a dy integral. Here, the axis is horizontal, so it's going to be a dx integral. And you could like what would even the slices even look like if you tried to do it dy? They would be really complicated. Like if you tried to slice a ring, not like along the finger, but how do I even do this? Like if you sliced a ring and you cut it here, like you would get, say, 2 disjoint pieces, unless you sliced it right at the top where you'd get just some sort of other weird shape. It would be very irregular and hard to, there wouldn't be enough symmetry for the problem to be worked out in any reasonable amount of time. So that's a good question, and in this case, that'll be part of the challenge on your homework, is to figure out what the appropriate variable to integrate is. So here it's x, and our cross sections here are what, if you may recall, I said earlier they're called annuli. I guess is the plural of annul. You don't say annuluses, it's annuli. Where if I have an annulus, let's say with inner radius r, little r, outer radius big R, with, so the area, it'll be pi times big R squared minus little r squared. In this case, or big R, so here's sort of the fun part here, is find what your outer radius is and find what your inner radius is. So if we're looking at this red disk here, the outer radius is going to be this guy right here. So there's going to be a lot of geometry in this. That's going to be 2 minus whatever the y value is, which is 2 minus 1/2 x squared. So that's equal to my outer radius, what I was calling big R there. The inner one, can anyone see what that is? It's actually constant. Yeah, it's 2 minus 1/2, or just 1.5. So that's the inner radius. Little r. Okay, so in this case, we get pi times 2 minus 1/2 x squared squared minus 1.5 squared. Thus, the total volume is, let's see, this is 1. This point right here is at -1, by the way. So it'll be the integral from -1 to 1 of pi times 2 minus 1/2 x squared squared minus 1.5 squared dx. Sometimes you can exploit symmetry of this problem even further. Like, I would like to point out that I could write this as twice the integral from 0 to 1 of the same integrand. Basically, I'm saying the half of this ring that's on the right side is the same as the half that's on the left. So that's going to save us a little bit of trouble. Any questions on that, why I was able to put a 0 here? You guys can kind of see it, right? So definitely, if you can exploit some symmetry to save yourselves some trouble, do it. And okay, do I feel like doing this integral? I guess I can do it. All right. So this is 2 pi times the integral of, okay, I'll get a 4 minus 2x squared plus 1/4 x to the 4th minus 1.5 squared. So I get a 2 pi 4x minus 2/3 x to the 3rd plus x to the 5th over 4 times 5 minus 1.5 squared x from 0 to 1, which is equal to 2 pi. I always love it when you get to just plug in 1 in evaluating an integral, because you can kind of just like forget about all the x's. Yeah?
Isn't it just x squared?
Sorry?
4 minus x squared?
This one?
Yeah.
2 times. We get 2 of them. All right? That'll be minus x squared. All right? A minus b squared, it's a squared minus 2ab plus b squared. So I think it's 2 minus 1/2, and then there's 2 of them. Okay. So we get 4 minus 2/3 plus 1 over 20 minus 1.5 squared. And, you know, whatever that is. I don't really care. Any other questions? Yes. That was the 4 times 5. Like I was saying about plugging in 1 when you're evaluating an integral, it's pretty easy if you just, because if you plug in 1 for all these x's, it's just 1, 1, 1, 1. So it's pretty easy like limit to plug in. And plugging in 0, you get 0 in all the terms. So that's why I did that kind of fast. All right. Well, It's, I think we can end early today, Friday the 13th. Wait. One question?
I was going to ask how you got the
The what? That, hey guys, hold on one second. It's just, that's the distance from here to here. And I gave you the formula for this point is y equals 1/2 x squared. So it's the difference between these two y values.